This is Ms. Black with Open Campus, and we are in the second part of Module 10. The first part, we looked at a definition one-to-one related to functions. So in this Module 10b, we're going to look at another definition called inverse functions. So if you do, please go to your class notes. Okay, so if we look at our notes, we have this definition of inverse. The word inverse means with functions to switch the domain, the x values, and the range, the y values. Now, what's very important for you all to understand is that you've heard the word inverse before in math. You heard it back in elementary school and all through algebra. So I want to make sure you understand today's word inverse, even though it's written the same way and it's said the same way, means something different when you're dealing with functions. If we go back into your experience with math, you've heard the words additive inverse and multiplicative inverse. Both of those words you heard in elementary school all the way up, especially through algebra. And when we use these words, additive and multiplicative with the word inverse, it has to do with numbers, real numbers, any number, whether it be whole number, positive, negative, fractions, decimals, any number has an additive inverse and a multiplicative inverse. So let me just refresh your memory of how you've already heard the word inverse used before. Let's take, for example, the number 5. So everybody, let's close our eyes and visualize. There's a number line, and we are all standing at the number 5. And we all know 5 is technically 5 units to the right of 0 on the number line. Well, we can say in math, every number that's on the right side of the number line has a number it matches up with on the left side of the number line. So just like in elementary school, if I said move 5 to the right, to do that opposite, I would move 5 to the left. That number that's opposite of 5 is called the additive inverse. And that's what it means. Additive was fancy for the word add, and inverse meant opposite. So you all know from your elementary school experience, the opposite of 5, the additive inverse of 5 is the number negative 5. Because positive 5 is 5 to the right of 0, negative 5 is 5 to the left. Okay, so every number in math has an additive inverse except for which number? Which number does not have an opposite? Very good, that's 0. 0 is neutral. There's no opposite of 0. Okay, every number on the number line also has what we call a multiplicative inverse. Now think, multiplicative is fancy for the word multiply. What operation goes hand in hand with multiply? That's correct, it's divide. So every number has a multiplicative inverse. So if I start with the number 5, the multiplicative inverse of that would be its reciprocal. Now you've all heard the word reciprocal before. You heard it in 5th grade. It has to do with a fraction. And in slang words, reciprocal means to flip the fraction. So if I have the number 5, which is 5 over 1, and then I do its reciprocal, I flip it, it becomes 1 over 5. Well, when you have 1 over 5 or 1 divided by 5, you've now done the opposite of multiplying. So the reciprocal is called the multiplicative inverse. You're doing the opposite of multiplying, you're doing division. That's great. So we've heard the word inverse before with numbers. Every number, you can add its opposite, which is the additive inverse, because the opposite of adding is technically subtracting. And every number, the opposite of multiplying is dividing. That's where you get the word reciprocal. Because when you have a division bar with a fraction, we're doing the opposite of multiplying. We're dividing. In graph land now, we're dealing with functions. We're graphing. The word inverse does not mean the same thing. When we're dealing with graphing and pictures of functions, the word inverse means switching the domain and range. Domain is your x value. Range is your y value. Now, when I mean switch their locations. I don't mean make them the opposite. I'm not saying do the additive reverse. I'm not saying making them the opposite sign. I do not mean make them the reciprocal. I'm not saying to make them fractions. In graphing, the word inverse means to physically switch the x value and the y value. Whatever number's in the x spot, now is going to go in the y spot. Whatever number's in the y spot is now going to go in the x spot. And that's what your definition of inverse means today. It doesn't mean the same thing as it did when we dealt with numbers. In graph land, inverse means take all the x numbers, they are now the y's. Take all the y numbers, now they become the x. There's a special notation for inverse. Instead of us writing, tell me the inverse, and writing the word, we are going to use a -1 in an exponent spot. I know that sounds crazy, but that's what mathematicians came up with. So if you see a -1 in the exponent spot on a letter, it means to do the inverse. So if you look here at my example, I have a point. A is -1, 5. It has an x value, it has a y value. If I want the inverse of A, which is written A to the -1, that means in words the inverse of A. That little -1 exponent means the word inverse. When I see that, it's telling me switch the x and y value. So the x value, -1, is now the y value, and the y value, 5, is now the x value. So if I give you the point -1, 5, and I ask you for its inverse is 5, -1. That's all the word means in graph land. Inverse means switch the domain and range. All right, so if you look here, guys and gals, I have 3 points, 3 ordered pairs, 3 relations. If I ask you to do the inverse of these, all I'm asking you to do is switch the position of the x and the y's. So what happens here is I'm going to label all the x's. They're always the first part of the ordered pair. I'm going to label all the y's. When I ask you for the inverse, all I'm asking you to do is switch them. So instead of writing 0, 4, we would write 4, 0. Instead of writing -2, -3, we're going to write -3, -2. Instead of writing 5, 0, we're going to write 0, 5. And that's what we mean today by the word inverse. When you're dealing with graphing and points, inverse means switching the x and y's, the domain and range. Now, instead of using the word inverse, they're going to use this little -1 exponent. So that -1 exponent means the word inverse in math. Okay, it's not connected to a number. So that -1 on a variable means the inverse with graphing. All right, now that's great when I give you the x and y's as points. But what happens if I give it to you in function notation, if I actually give it to you written in algebra? So look at my example 2. F of x equals 2x. That's my function. Here is Fred. We've already discussed this. Every time we see Fred, we're going to replace him with the letter y. So that's really y equals 2x. That's a graph. In case you don't know, because that has an x and a y, it would be a graph of a diagonal line. A diagonal line has many points on it. Well, you can't sit and list every point on a diagonal line and then physically switch their x and y numbers to make the inverse. So look at me. If you're given the points like in example 1, it's very easy to switch the x and y's. But if you're given an equation and I want its inverse, you're going to do the same thing. You're going to physically switch the letters x and y. Because this x means all the x values of the points. This y means all the y values of the points. And inverse means to switch them. So now this new equation is going to be, instead of writing y, we're going to switch it, we're going to make it x equals 2. Instead of writing x, we're going to write y. Now the problem with this equation is they're not going to accept it. When they want the inverse equation, they want it solved for y. So now you got to do some of your skills from solving and get y by itself. So the first thing I'm going to do is flip this equation around. I'm going to write it as 2y equals x. And now I'm going to get y by itself. I'm going to divide by 2. So this equation is y equals x over 2. Or I could write that as 1 over 2 is 1/2 x. That is the inverse equation. And right here, if you look here, it doesn't say f of x. It doesn't say Fred anymore. It says the inverse of Fred. This still stands for y, but it's saying give me the inverse equation. Well, here's the inverse equation. Y equals 1/2 x. So our definition today is inverse. When you're dealing with functions, equations, and you're dealing with graphing points, the word inverse means switch x and y. X is called the domain, y is called the range. If I actually give you the points, it's very easy to switch the numbers. But if I give you an equation, then I'm asking you to switch the letters. So let's try another one like this, where you're given the equation. All right, let me get my notes. All right, our next equation is f of x equals 3x minus 4. And they want us to come up with the inverse equation. First thing, even to talk about the word inverse, you need to have x values and y values. Well, I see my letter x. So where does my letter y go? We've discussed this. If you see function notation, Fred, you always replace it with the letter y. Now, we're going to do the inverse. Inverse means to physically switch locations. Put the x in that spot, put the y in that spot. That's all we're going to do. So instead of writing y here, we're going to write x equals 3. Instead of writing x, we're going to write y minus 4. So far, so good? The problem is they don't want this equation equal to x. They always want your equation equal to y. So now we got to solve it. We got to get y by itself. So do you agree to get y by itself? We can add 4. X plus 4 equals 3y. Is y by itself? No. We got to divide by 3. We divide everybody by 3. This is x over 3, which is the number 1 over 3. So this is 1/3 x plus 4/3 equals y. So now I'm just going to flip that around. It should say y equals 1/3 x plus 4/3. That equation is not like the original equation. Everybody look at the original. Y equals 3x minus 4. Now look at this equation. 1/3 x plus 4/3. It's not the same. They are inverses of each other. What's going to happen is your homework's going to say, or in your book, it's going to say f negative 1x. You got to understand f of x, Fred, the negative 1 means the inverse equation. Here's the inverse equation. The letter f of x still means what the letter f of x here is. It means what the y is. So you got y by itself, so that's what you're going to type. The inverse equation is 1/3 x plus 4/3. That's why you got to get the y by itself. Once the y is by itself, then you can tell what the inverse is. Okay? Let's try another one. Okay? So I'm going to give you an equation. Here's my equation. F of x equals x plus 2 cubed. I want the inverse equation. Well, if you ever hear the word inverse and we're dealing with functions and graphing, what you got to do is see an x and a y. I see an x, but I do not see the y. Every time you see the function, cross it out, put the y. All right, now we're going to make the inverse. Inverse means to physically switch the letters. So this x is going to go there, and this y is going to go there. So we're going to write here x equals, parentheses, now we're going to write y plus 2 equals 3. That's the definition. You can't think about it. It's a definition. You've got to take it for what it means. Inverse means switch the x and y. I can't leave my equation like this because they want every equation to have y by itself. So now you got to get y by itself. Well, you can't move the 2 because it's stuck in parentheses. We got a cube. How do we get rid of a cube? That's right. We do the opposite. We do the cube root. So this says the cube root of x equals. Cube roots and cubes are like squares and square roots. They cancel out. Is y by itself? Nope, we got to subtract 2. When you subtract this 2, can you stick it inside the grouping symbol? No, you cannot. So this would be the cube root of x minus 2 equals y. And I'm going to write it the way I like to see it. Y equals the cube root of x minus 2. Now, what they're going to have, what you're going to see, is they're not going to say, what's the inverse equation y equals? They're going to say f negative 1 of x. The negative 1 exponent means inverse. And all they want to know is what y equals, because f of x stands for y. Well, y equals the cube root of x minus 2. You made the inverse equation. Okay, I think we have one more. Let's try the last one. Okay. So again, we're learning a definition. Our new word is inverse. Equation D. F of x equals square root of x. So I have that equation. F of x is the square root of x. First of all, every time you hear the word inverse, you got to see an x, you got to see a y. There's the x. So this right here, function notation, always gets replaced with y. Now that you see your x and a y, the word inverse means to switch their locations. So this x is going to go here, this y is going to go here. The only thing you're physically moving are the variables. You're not moving any symbols, no other numbers, just the variables. So this is going to become an x equals the square root symbol stays, inside goes the y. Now I can't keep that. I got to get the y by itself. How do you get rid of a square root? You do the opposite. You square both sides. So this is going to become x squared. Square roots and squares are opposite operations. They cancel out. There's your y. So this says y equals x squared. So again, what's going to happen is they're not going to say what is the inverse equation and say y equals. They're going to say what's the inverse equation. They're going to have f of negative 1 of x. You've got to understand this little negative 1 exponent means inverse. F of x still stands for y. There's your y. There's your inverse equation. It equals x squared. Is everybody okay with the definition? All inverse means is switch x and y. Okay, let's go to example 3. Our next example. Our next example says, part A, find the inverse of f of x equals 2x minus 1. All right, well, that's what we just learned how to do. So let's try it again. So again, inverse means switch x and y. When you're dealing with functions and function notation, inverse means switch x and y. I'm looking here. That's my function notation. That's the letter y. So I have y equals 2x minus 1. I see my x, I see my y. Okay, I'm going to switch them. So now my new equation is going to be x equals 2y minus 1. But can I leave it like that? No. Every equation, y has to be isolated. So let's get y by itself. Let's add 1. X plus 1 equals 2y. Is y by itself? Nope. We got to divide by 2. So we divide every term by 2. X over 2, well, there's an invisible 1 in here, so this is 1 over 2, which is 1/2 x plus 1/2 equals y. I'm going to just flip that around, so write y equals 1/2 x plus 1/2. This is the inverse equation. But instead of keeping the y, they're going to replace the y with f of x. And because it's the inverse equation, they're going to put the little negative 1, so you know it's the inverse equation. So it equals 1/2 x plus 1/2. Now, part B says, on the same graph papers, the same coordinate system, graph the original and graph the inverse. So now we're going to draw a picture. So now we're going to relate this to graphing, which you did back in Algebra 1. You should remember from Algebra 1, when an equation has an x and a y, it's a diagonal line. Okay? Diagonal line. To graph a diagonal line, your equation is supposed to be in slope-intercept form. You all heard that before in Algebra 1. Slope-intercept form is y equals mx plus b. So to graph a diagonal line, you want the y isolated. There's the y isolated. Right here. Here's the y isolated. When the y is isolated, there's a number connected by multiplication to the x. There's a number behind the x. And those are the two numbers you use on the graph paper. These two numbers have names, vocabulary words. You should remember M means the word slope and B means the word y-intercept. So, from Algebra 1, just to refresh your memory, we're about to draw a picture of this equation. Every equation you could draw a picture of. To draw this picture, I know it's a diagonal line because it has an x and a y. Because think about it. When you draw a diagonal line, it will touch the y-axis, it will touch the x-axis. To graph it, I only need these two numbers, the 2 and the -1. But how do you use these numbers? Well, that's why the vocabulary words are important. This number 2 is called the slope. This number -1 is called the y-intercept. The way you use them is based on the words. Slope is your movement of your line. The word slope in French is mentir. That's where the M comes from, because it was a French mathematician that came up with this. And mentir means movement, how to move. Well, we can't use this yet. We can't use the 2 yet to move because we don't even have a starting place. The B, the number that's behind this -1, stands for the y-intercept. And if you remember, a y-intercept is where you touch, you intercept the y-axis. So we go to -1 on the y-axis, and then we're going to use our slope, our number, to move. But to move on this graph paper, you have decisions. You either can move left and right, and you can move up or down. The way you decide how to do that is you take your slope number, 2, you write it as a fraction, 2 over 1. And if you remember your vocabulary, slope is rise over run. We're going to rise 2, we're going to run 1. So from here, I want you to rise 2. Well, that means to go up 2, 1, 2. I want you to run 1. Run means go to the right 1. And you can do that as many times as you want. Up 2, rise 2, run 1. Rise 2, run 1. Rise 2, run 1. The reason why we're running to the right is 1 is positive. And the positive numbers go to the right. The reason why we're going up is because the positive numbers go up. And that would make that diagonal line. And we would call that f of x. That's your original, Fred. Now they want you to graph its inverse. So again, to graph an inverse, I need the equation with both the y and the x. Here it is. Because it has both the y and x, it's going to be a diagonal line. I need to see the two numbers. I need it in this form, slope-intercept form. It is y equals. Here's my m, x plus, there's my b. Again, m stands for slope. Slope is moving. I can't move yet. I can only move once I plot a point. This number behind, the b number, is called the y-intercept. This is where you go on the y-axis. So we're going to go to the y-axis to 1/2. Well, 1/2 is a fraction, and it's in between 0 and 1. So remember, these are number lines. Our number lines are not just whole numbers. Everywhere in between are fractions. So I begin at 1/2. My slope says to move 1/2. To move 1/2, we're going to do rise and run. That's a straight rule. We're going to rise 1. We're going to run 2. So here I'm at 1/2. I'm going to go up 1. So if I'm in the middle of a box and I go up 1, I'm still in the middle. Now I'm going to run 2 to the right. 1, 2, put my point. I'm going to do it again. Rise 1, run 2. Rise 1, run 2. And now I'm going to make my other diagonal line. And I'm going to name this one f negative 1x because that's my inverse. So what I did on this graph paper is I graphed the original equation, the original function, and I graphed my inverse function. Now if you look, I'm going to throw out a big word to you. There's some symmetry here. Symmetry means looks the same. Like the human body, we have symmetry. Our right side and our left side look the same. So when you graph, there's sometimes symmetry, ways things look the same, which means if you folded them, they would fall on top of each other. Do you all agree if I took my arms and I folded my arms together, they would match up? Okay, that's called vertical line symmetry because I'm standing up and down. I'm vertical. So our bodies have vertical line symmetry. What you're looking here is at this picture of the original and the inverse. There is some symmetry here. There is a way to fold this so the two lines would fall on top of each other. And what we would say is these lines have diagonal line symmetry. If you took this piece of paper and took this corner and folded it over to that corner, the two graphs would fall on top of each other. They would cut across this diagonal line. So I'm going to draw this diagonal line right through the middle of the graph so you can see it. Okay, so in black, I'm going to draw a diagonal line that goes right through the whole graph. I know I'm doing it freehand. I apologize. It's not perfectly straight like it should be. But there is that diagonal line. Do you agree? If I took this blue piece of the line and I folded it over, it would fall there on the purple. And if I took this purple and folded it over the diagonal line, if I creased it right here, it would fall on the blue. Every time you graph a function and its inverse, it will always have this diagonal line symmetry. And this diagonal line's name is y equals 1x plus 0. And the reason why is, look, it begins on the y-axis at 0. Its movement is up 1 over to the right 1. Up 1 over to the right 1. Now, we know in algebra, is the 1 necessary to write in front of the x? No. So we can write y equals x. And in algebra, is adding 0 going to change this? No. So we would say every time you graph a function and its inverse equation, every time you draw a picture of them, they will always have diagonal line symmetry, y equals x. And that's important. All right, we have one more concept. Let's go back to our notes. So now that we went over how you write an inverse equation by switching the x and y, we want to be given two functions. And we want to know if they're inverses. One way to find out if they're inverses without graphing them is to do a test. And in your notes it says here, to verify two equations are inverses of each other, you will do f of g of x equals g of f of x. And when you do both of those compositions, you should get out the letter x. So, from the previous module, in 9, we learned a composition. A composition is when you take a function and substitute it into the other function. So what we're going to do here is we're going to have two functions. F of g of x means to start with g of x and substitute that into f of x. The second part, g of f of x, means to take the function labeled f of x, Fred, and substitute him into g, which is Ginger. And when we do both of these substitutions, if they both give us the letter x, we have now proved that those two functions are inverses of each other. So that's why we had to learn how to do a composition. Again, if you look at the notation, f of g of x and g of f of x does not mean to do the same thing. You work from the inside out. The first part, f of g of x, means start with x, substitute it in g, Ginger, get your answer. Then take that answer, substitute it in f, Fred. The other part, g of f of x, means to start with x, but now you're going to put it in Fred first, get an answer. Take that answer, substitute it in function g, Ginger. If both of those answers come out to be the letter x, That is how you verify that your two functions are inverses. Okay, let's go to the whiteboard and try our last example. All right, so everybody look here. They're going to give us two functions. So now I'm going to give you the two equations. I'm giving you Fred, 10, 100 plus 12x, and I'm giving you Ginger, x minus 100 over 12. And I'm asking you, are these two functions inverses? We could take each one of these and graph them like we just did a minute ago and decide if they have this diagonal line symmetry. But that would be a lot of work because look, we got a number 100. And do you want to do a graph paper with 100? No. So there's got to be another way on paper. How do we prove if these two equations are really inverses of each other? Well, there is a rule. In your notes, the rule says f of g of x equals g of f of x, which equals x. Now you're going to say, I've seen that before. You sure have. In Module 9, that open circle meant a composition. What they're saying is, you can tell if these two equations are truly inverses and not have to draw the picture and see if they fold on top of each other diagonally. I mean, we could do that, but it'd take a lot of work, and a graph to 100, well, I don't have enough space here. My graphs only go up by 10. So the way we do it on paper is we do a composition. And that's why Module 9 had to come first. We had to learn about this word composition before we could talk about inverse. So let's recall how you do a composition. F of g of x means you start with the letter x. You substitute it in g. So here's g. It's already got an x in it. That part is already done. So we know what g of x is. G of x is x minus 100 over 12. What we're going to do is take that and now substitute it into f. So if we go up to the top here, f of x equals 100 plus 12x. We're going to take this, what g is, that function g, and put it in the spot for x. So now we're going to do some algebra. We're going to write 100 plus 12. We're not going to write x. We're going to write this lovely fraction, x minus 100 over 12. I know what you're thinking. Oh my, we can do a lot of algebra here. No, we don't. Because you all know, do you add first or do you multiply first? Well, we know we multiply first. What happens if there's a number in the numerator and a number in the denominator is the same? That's right, they divide out. So now we have 100 plus x minus 100 because the 12's canceled. That plus is not going to change what's inside the parentheses. So now we really have 100 plus x minus 100. And 100 minus 100 is 0. And we're left with x. Now we're not done. To prove that these two functions are inverses without drawing a picture, now we have to do the composition the other way. And if you remember in Module 9, we said compositions are not commutative. They shouldn't come out to be the same. So if they're truly inverse equations, what's going to happen is when we do the other composition, it will come out to be the same as this one. And that's important. If you do the composition both ways and you get the same value, you are an inverse. And the value we're going to get out both times should be the letter x. So now let's do it this way. This says g of f of x. So again, what are we starting with? X. We're substituting it in f. Well, that's already done. If you come up here to f, it's already got an x in it. So we're taking this. We are taking 100 plus 12x, and we're going to substitute that into g. So we're going to write g, okay? G of x is x minus 100 over 12. Wherever there's the letter x, we're going to put 100 plus 12x. So that's going in this spot right there. So there's the x. We're going to cover it up. We're going to put 100 plus 12x minus 100 over 12. So all we're doing is rewriting it. There was the x in Ginger. We're covering it up and putting function f. Well, in your numerator, 100 minus 100 cancel out. Now you have 12x over x. Well, now we're connected by division This is multiplication, so 12 over 12 divide, and you get x. When you do a composition both ways, f of g of x and g of f of x, and both times you get out the letter x, you have now proved that these two are inverses. And that's your rule. So that's why you had to learn compositions first. A composition is a way to prove that two equations are inverses without having to draw a picture. And that finishes up our definition of inverse. I'll see you in the next module.